Hey everyone, hope you guys are all cozied up, got your good lunch in, and re-upped on some coffee because we got some exciting things to show for. Welcome to BWP304, fast evolving GraphQL schema with Federation. Now, if you're in the wrong session, well, security locked the doors because we've locked you in for a whole hour. Lucky or not lucky, we got really cool information to share. Here shared with me on the stage, two amazing individuals, the BWP finest. I'm Joseph, Solutions Architect. I have David and Matt, and I'll let them give a quick intro.
Sure. I'm David Ramos. I'm a principal engineer with Amazon with the BWP team. I've been with Amazon like 13 years now, so happy to talk about that over drinks later on.
Hi, I'm Matt Quinlan. I'm a senior software engineer with Amazon. I've been with Amazon and in the US for about 6 years, and BWP doing GraphQL APIs for about 3. If you detect an accent, it's not British, it's refined Australian.
Cool. Again, I'm Joseph. These guys are just making me look good on stage. So awesome. We'll just roll in right into the presentation. We'll start off with a quick agenda, BWP, quick introduction for those who don't know. And then I'll hand over the baton to Matt over there to talk about our GraphQL schema federation. And then Matt will hand off for David to close out, mic drop. And if there is time remaining, sorry about that. If there is time remaining, we'll leave it for Q&A. If not, you can catch us at a bar, happy hour, or even outside if you want to learn more about BWP. All right, so BWP. Before we gauge in, I want to get a quick interaction from the audience. Who here has a Prime membership, knows Amazon.com, or has shopped before with Amazon? Okay, I think that's everyone here. So here at BWP, what we're actually trying to do is externalize Prime outside of Amazon.com. So if you have a favorite merchant or your even favorite D2C store, you can see that Prime logo right on the customer user interface of the website. And what does that look like? Right there. So you'll see that familiar Prime logo, you'll get that delivery promise, and along of the other benefits that you have with Amazon, such as the customer service, seamless returns, and all of that for that nature. Now, according to the data, we've seen that Prime, or BWP, provided many benefits to existing merchants that have already integrated with us in our technology. So the data right there, about 20% in shopper conversion with merchants enrolling or integrating with BWP. And then on average, merchants, we saw that 3 out of every 4 orders were actually BWP orders. So attracting new shoppers, getting engagement for a merchant that is integrating with the service that we offer here. So a huge benefit to not only to the merchants, but also to shoppers that they attract to their storefront. So it's a win-win. Again, increased shopper conversion. We offer that Prime delivery that you guys all are aware of, returns and customer service, and many more other offerings. And feel free to check up into our website on BWP. But behind that badge and behind that user interface experience that you've seen displayed on the merchant's website, it requires a lot of technology, a very intricate, complex integration that happens behind the scenes, underneath the hood of what you see that logo to be. And a main component of our BWP API is our GraphQL service. And because of our GraphQL service, customers, they can interact with BWP programmatically via our API. It enables our customers to accelerate the business by, again, offering that Prime service outside of Amazon.com. And with our API, customers can import their catalog with products. They can display that estimated delivery speed, query orders, sync returns, and returns. And the list goes on. So that's a quick high level of Buy with Prime. And again, for more information, feel free to check out our website or catch us outside of this presentation here. But I'll pass it over to Matt to deep dive behind our GraphQL service and all of the intricate parts.
Thanks, Joseph. So how did we provide a single GraphQL API for our Buy with Prime? And importantly, how did we manage to deliver a scale for all these different backing services and manage the release quality as well? And how do I support my different customer types? So in Buy with Prime, we have managed customers, SaaS customers, and bespoke integrations, all with their own requirements. And we want to make sure that the API that we're delivering to them evolves predictably and without breaking their experience. And behind all that, we have several backing teams. And we want those teams to be able to operate independently and scale and deliver to our bespoke set of customers. So we chose GraphQL because it's a good model for composing these APIs together. It allows us to have strong type definitions for our types and a very predictable experience for the customer. GraphQL is a very strongly opinionated spec. And it allowed us to combine all these contributions from our different teams. But when we were trying to support all these different customer types and roll out our Buy with Prime product rapidly, we had problems around managing schema changes, managing the federation of that schema, and doing release management as well. So I'm going to start with the schema changes problem today and talk about how we solved that. And to talk about all these problems today, I'm going to start with a simple example, and I'm going to build on it as I go through. So my simple example to start with is I have a product type. It has a title, price, create date, last update fields. I have a query on that product, and I have a mutation to create an order using that product. And I'm going to start with just the product itself. So we're going to make some changes and see how this plays out. So the first typical change you would do is add a field to the GraphQL type. And this is pretty standard, and it's generally backwards compatible. I can add fields because customers are only ever requesting what they want. No customer is currently requesting a description field if I add it. And I'm not going to break their experience. Even if that customer is using a very strict form of deserialization for their response, this is essentially non-breaking. This gets a little bit more complicated, though, when we start doing other things. So what if I wanted to remove fields? If I wanted to remove both the date fields and the customer was, say, still requesting them, they're going to get a 400 bad request error. I would need to kind of communicate to the customer in advance and say, hey, we're going to deprecation these fields. I want you to stop using them. I need to monitor the requests, make sure they are not using them before I remove it. This can get even more complicated again. What if I wanted to change the type of the fields? So let's say I wanted my create date and last update to not be ints, but to be strings. This is incredibly complicated to manage, and it gets even more complicated when I have more customers and more fields that I want to change at one time. If I wanted to change these field types, I'd have to get customers to migrate to a new field, make sure new customers are not using the old field. I'd have to potentially just create a new name for the field because managing type change is incredibly complicated. And then even communicating to a broad customer base is hard. How do I communicate to customers who may not be monitoring emails or may not come and check the API spec? As a dev, kind of once you've built your integration, you don't revisit the API page every now and again. So to attempt this kind of migration, I need some kind of versioning system. And GraphQL takes a strong opinion on avoiding versioning. That makes it kind of hard. So thank you, everyone. Sorry, bad jokes aside, I've only got one bad joke today, I promise. Actually, I don't think I have any more jokes, so we're all good. The GraphQL spec is actually super helpful. It has a lot of really good advice in there. One about delegating authorization. So we do that in Buy with Prime. It makes it a lot easier for us. And they say there's a lot of cross-cutting concerns where they're unopinionated or they give you kind of the option. And so while they take a strong opinion on avoiding versioning, we do have the freedom to do that ourselves. So let's have a look at how we might version our GraphQL spec and what those options are. And to understand what those options are, we'll consider kind of two things: the number of clients we have and the volatility of the API. So how frequently is our API changing? If you have a very small number of clients, 1 or 2 clients, and your API is not changing frequently, then the recommendation from the GraphQL Federation is pretty much spot on. It's easy to manage. It's easy to kind of change and communicate with those clients and be hands-on with your customers. But when your number of customers grows, number of clients grows, and communicating with those customers becomes more difficult, you can't readily evolve the schema. And so what you might do is you might just create a new schema and a new endpoint, and you might have a V1 endpoint and a V2 endpoint. And this is potentially manageable if you're not rolling out API changes frequently. So if you're doing them in the order of once a year or once every 2 years, you may be able to absorb the cost of kind of spinning up new APIs and the maintenance on those APIs. But if you have a high volatility API, so in with Prime, we're learning about our customers every day. We've had to make frequent changes, roll out new APIs, meet the needs where they are, and we've had to come up with something else to kind of solve this versioning problem. And we call it schema projection. And so what schema projection essentially is, it's a configuration that sits between your schema definition. It's a small build tool that uses the projection config to then produce a set of version schemas. And so I'm going to use our original example with the product and kind of go through what that would look like. So we have the product here, and version 1 was the product version with just title, price, create date, last update. And version 2, we've made a couple of changes. We've added a description field, and we've changed the type of the create date and last update from int to string. And so what we will do is we will create a base schema that contains all this information. And I can use this base schema to then generate these version schemas. So to dive into this base schema a little bit, I've added 2 new authoring directives. I've got an added directive and a remove directive. So I've added my added directive onto the description string to say that from version 2, I'm going to include description. And my create date, I'm going to remove create date and last update because they were ints. And I'm going to add create date string and last update string, which are now strings. And I'm going to alias those names back to create date and last update. And so why this might seem a little bit more verbose than managing a single schema, it allows us to kind of reuse our base schema, reuse this base type definition. It increases the discoverability of changes, so engineers who are working on this type definition are only seeing one type defined in one place and all the changes that apply to that type. And the third one is we can actually use this type definition when we write our data fetcher and resolver code to support the multiple versions. So I can write a data resolver that returns all these fields optimistically and then use that to meet the client's query, which I'll get into in a moment. And so what we next have is the actual configuration itself. And this is just an example configuration based on the previous slide. And this projection configuration shows a definition for a product version 1 and version 2. And we just use that version 1 and version 2 and the previous base schema to produce our versions. And so the versions are produced here. This is what we wanted. This is our output. And you'll notice that there are a couple little additions on the version 2 page, the version 2 definition. So on that version 2 definition, we've got this new source directive. And so whereas the added and removed directives were authoring directives, our source directive is an execution directive. So it's at runtime, it has meaning. And so what we can do is we can use this source directive and take advantage of the default data fetcher concept in your GraphQL libraries to make some kind of generic or reusable decisions about how to serve a customer's request. So let's look at the default data fetcher. And to do that, we'll just use a simple query example. So imagine a customer is querying for a product with a title and a create date. So what typically happens in GraphQL resolution is it resolves from a parent to child, siblings in parallel, nested fashion. So what would first happen is you would resolve the query and product definition, and then you would resolve the title and create date on that product. So let's explore the default data fetcher concept. So what would happen in a typical GraphQL library is anytime you're trying to resolve something, you would check for, does a custom data fetcher exist? And so if we're looking on the query for a product, this is our root level operation. We're incredibly likely, or almost 100% like going to have a custom data fetcher here to resolve the product. And so we will find one and we'll use that custom resolver. And because we had our base type definition before, which contained both version 1 and version 2 attributes, we can optimistically resolve those attributes using this data fetcher. Next, we'll look at the subfields of the product type. And because we haven't created a custom data fetcher for this, we'll use a default data fetcher. And we've overridden the default data fetcher to do one little additional thing, which is say, is there a source execution directive associated with this field? In the title case, there's not. We haven't modified or changed the title across versions, so we just resolve title via the property name. In the create date case, though, this was changed in version 2, and we included a new source directive on it, and we've said, hey, when you encounter this during execution in the default data fetcher, go and find that via create date string. So we'll look for the create date string that was populated and use that to return the customer's request for create date. So just to summarize, I guess, the versioning aspect of this story. So by defining a single base schema, we've allowed teams to define or see changes in a single place for the type they're managing and writing across versions. This also consequently allows us to create, I guess, a single data fetcher for that version as well. So I can optimistically return the entire type and rely on the default or generic data fetcher to manage that return type across versions. And then this allows us to develop schemas that are specific to the client experience. As I said before in with Prime, we've had to rapidly adopt our schema changes for different clients, and we can now manage those versions and see those changes in one place. So now we've got a way to version our schema, but how do we manage that across all our different backing services? So we have a lot of different teams in with Prime managing the customer experience, and they all operate independently. So how do I manage their ability to kind of author these schemas, test these schemas, release them? So I'm going to return back to our simple definition. So we have our query and product mutation, and we have our product definition that has now been updated for our version 2 management and has the version 2 authoring directives. And I have a very simple infrastructure over here. I have a GraphQL API, and I have my product and order backing services. And these services are pretty much independent right now. The GraphQL API itself is doing the hard work of data resolution. So let's add a little bit of complexity to this. So I'm going to introduce a new service. I'm going to introduce the inventory service. And inventory is essentially an extension of product. So I have inventory on a product, and I can define it in a couple of different ways. I could use the GraphQL spec itself to say, hey, let's extend type product, let's add inventory, and I have this inventory that has an ID and quantity. Or I could use some kind of annotation or directive-based federation framework and put, say, an extends on a product and have some custom build logic around, hey, this inventory extends someone else's definition of a product. And then I can have the GraphQL API just delegate requests for inventory to the inventory service. This traditional model had a couple of issues for us. The first one was that the product microservice needed to operate independently and be an independent offering outside of our composed API. So I should be able to make calls to the product microservice and get inventory information without having to get routed through our composed GraphQL API, because our product service may support other use cases somewhere else. The next one is that the resolution of inventory is somewhat coupled to product schema in the way that the resolution works. So there's kind of an assumption that when I resolve inventory, I'm resolving it with some understanding of what the product key is, or I have a product ID that I'm resolving inventory on. But that relationship might be inversed. My product might have some inventory key, and it knows about inventory, but inventory doesn't necessarily know about product. And the real problematic one is that when I start extending and federating my systems and connecting and composing them like this, testing and deployment becomes very complicated, and I block a lot of the time. If I want inventory changes to get out to my composed layer, I need to make sure they work with product, and they don't kind of get tested until they get into that composed layer. So I've maybe federated my authoring, but not my CI/CD. So to solve some of these problems, we are pushing down the GraphQL composition and GraphQL service layer as well. So I don't just have a composed layer at the top. I have a composed layer at certain nodes in the system. So I have a composed layer sitting in my product service that is responsible for handling the product inventory queries, and the composed layer can take advantage of that. One of the biggest advantages of this is the ability for CI/CD and testing. So product can manage and develop its inventory relationship independent of the composed API. It can make sure that everything is running fine before going out as release. But one of the, I guess, disadvantages of this is I've added a new service into my domain service layer. But before I get to that, the other thing you can do as well is you don't just have to have a composed layer at the composed nodes. You could add GraphQL reverse proxies in all these nodes. So every service has its resource-oriented service system and its GraphQL-oriented service system. So how do I manage this, I guess, increase in compute? So we have a Fargate-based system. And so what we're doing is, or what we can do, is we can rely on the ability to run multiple containers within a single Fargate task. So I can put my GraphQL container, which is a configuration-driven reverse proxy. I can kind of write it once and plug it in everywhere. And I can have my backing service container, which is more custom. And in Fargate, I can take advantage of the elastic network interface, which basically has 0 millisecond latency to communicate between these systems. So I'm not incurring a latency cost. And because these are the same containers within a task, my compute cost is not going up as well. The downside to this approach is that the GraphQL container and backing service containers, because of the same part of the same task, they scale at the same rate. So while I can give them their own compute and memory footprint, anytime I scale up my tasks, they're both going to scale linearly together. So one of my options is to instead split these containers into their own services, but still running within the same cluster. This requires me to set up an application load balancer or a target group independently for each one, but they're sitting within the same VPC, and I can still route from my container to my backing service container with minimal latency cost. So that's the segue on the Fargate infrastructure side of things. So we've got our architecture. How do I manage the composition of the schemas, though? So I had my schema and my version schemas. How am I composing them together? So I'm going to walk through an example starting with the inventory schema, and I'm going to go to the product schema and then the compose schema and see how they all kind of come together. So this is our very simple product schema definition. They just have one version, and it's just extending the product type. And my projection configuration is very simple. I say I have one version, and it's version 1. And so the result is the output schema is one version, and it looks exactly the same as our input. We haven't changed anything. And so then product comes along, and we have our product definition. And our product has 2 versions so far defined in the base schema. And then we have our product definition schema projection configuration. And we've defined a new version. We've got version 3. And version 3 is going to include our inventory definition. It includes the configuration from inventory. And because all of our version annotations were from version, everything that applied to version 2 applies to version 3 here. And so now we've produced our output schema, which contains the changes in version 2, including a description and create date and last update, and now includes the composed inventory field as well. And then we can kind of keep doing that. So at our composed layer, we can include our product definition, we include whatever we define for order, and then produce our entire schema. Okay, so we've pushed down the architecture and we've pushed down the composition into the schema projection, but now I have a problem with call delegation. How am I going to call from my composed layer to my product layer to my inventory layer, which are all on different versions and different URLs? So we're going to add a little bit extra to our projection configuration. We can add a URL into the includes to say when you're resolving product, resolve it via this product URL. And then when we generate the produced schema, we add a new execution directive. So we had our source execution directive before. Now we have a remote execution directive. It basically says that when you're executing this product definition, execute it at this URL for this version. And we can take advantage of our default data fetcher that we had before. So our previous default custom data fetcher checked for a custom resolver. If not, use the default one, check for a source directive. And we can modify this slightly to say, well, before checking for a source directive, let's check for a remote directive. And if a remote directive is there and the data is not already populated, and because we're a push-down composition, it's possible that another layer has already populated this data using the remote directive, so we want to make sure it's not populated first. And then if it's not, we can use the remote URL to delegate that request to a downstream system. So what is the benefit we have out of this federation model? So we've allowed teams to independently define their schema versions, and they can own and manage their own schema release. We've allowed teams to compose the different schemas together, and different versions of those schemas can be composed in any way that sees fit. We've reflected this composition in our architecture, so we don't just have the composition in our schema projection, we've actually pushed down the composition in the architecture as well, so calls are delegated down the dependency tree. And it enables teams to do their own verification and testing, which is the really important benefit out of this, so our push-down team can validate all their changes before it gets to the composed layer. And then the final one is we've allowed, with our execution directives, our execution layer to be relatively generic or configuration-driven. So we can, this GraphQL reverse proxy system that we were putting in every Fargate instance for every backing service is just basically the same one and driven by configuration. And makes it, I guess, easier for our backing service teams. So now we have a federated architecture, and we can release those changes of our new versions. How do we ensure stability? It's currently the big problem. So in Buy with Prime, we had several early adopters. They had got onboarded to our API, and we kind of met them where they are with their needs. And as we grew our business and adopted new customers, they had their own needs, and we had to evolve our API to meet those needs. But we didn't want to break the existing customers. So we have the ability to version, we had the ability to federate, but how did we ensure we weren't breaking those existing customers and that they had a predictable and stable experience? So I'm going to revisit our example again. We have our product definition with its authoring directives, and we have our projection definition, which says, hey, create product version 3 and include inventory version 1 and route inventory version 1 to this URL. And we have our architecture, which is our push-down architecture. And let's simplify this architecture a little to start talking about the problem. So let's just focus on the GraphQL product inventory call. And let's simplify it again. Let's just think about the GraphQL aspect of this and not the backing service part of this. And then now let's add in a customer request. So the customer who makes a request for a product with inventory gets routed through the GraphQL API to the product API to the inventory API to get their essential inventory data. And these are our projections from before. So we had our product projection, which included, our composed projection, which included our product version 3, and our composed is on version 1. And then in the middle, we had our product version 3, which includes inventory version 1. And then on the far side, we had inventory version 1, being composed transitively, I guess, into the composed layer. And so when a customer makes a call, they make a call to the GraphQL API using version 1, indicating that they want the version 1 of the API. That gets translated to a version 3 call to the product API, which gets translated to a version 1 call to the inventory API. But what happens if the inventory team makes a change to their version 1 of the API? Whether intentionally or accidentally, what if they make a backwards incompatible change that potentially breaks the customer's experience? We've given the ability to kind of scale independently and own what they're building, but with that extra ownership, they now have the potential to hurt our customer experience. So what we've done to manage that is our projections now have this concept of a state. And the state can have semantic relevance for whatever you need. But for this example, let's just consider two states, a draft and a release state. And the release state has two significant properties that help us manage the safety of this release. we have two rules. Essentially, the first rule is a parent projection can only include released projections. It can't include a projection in a draft or any other state. And the second rule is that any change to a projection that has been marked with a release state will break our build. So we've added some custom build rules in there just when we compose all these together. If a change has been detected in the schema on something that is released, it'll break, and we have to figure out why and whether it's intentional and manage that change. But now we're catching that change at build time. So if the inventory team, the product team, and the GraphQL team now have a release state in each of their projections. And so the composed GraphQL API can only include the product API because it's in a release state, and similarly, the product GraphQL API can only include the inventory API because it's in a release state. But what if the inventory team did want to make changes? How would they go about that? Well, we can take advantage of our versioning system, our product projection composition, and projection release to manage this. So what would happen is inventory team would add their authoring directives, make their changes, create a version 2, and set it in a draft state. They can do their testing and validation on this draft state independently because they have their own GraphQL API. Once they're happy with the state of that and gone through whatever testing they need to do, they can then mark it as released. And this means that this API is now available and ready for consumption. So the product API is now available to consume this released API. They can create a product version 4 that now uses inventory version 2. They could have optionally increased the inventory, incremented the inventory on their existing one, but that was already marked released, so they would have broken their build. So it's easiest for them to say we have a new version. And again, the composed API can now say, well, I'm going to release a version 2 because I want inventory version 2, and I'm going to translate to get that via product version 4. The use of these version schemas, explicit composition here, has a real distinct advantage in terms of our rollout. So if we were to roll out without versioning, we have to sync these changes on these disparate systems. When I roll out on my subgraph, I could potentially have a customer who is making a query that is not ready for it, or my composed API needs to have synchronous deployments of schemas, which is really kind of hard to manage. This allows us to have more sequential rollout of what we're doing. So I'm going to summarize the key takeaways of these schema changes, versioning, and release management. So first is we have a single base schema. All the changes are authored and managed in that schema. We can see how it evolves. We can track and manage it in one place. The second is we created a projection to be an abstraction or reference from the base schema. We define a set of rules on that projection to produce our version schema. So from our projection, we produce our version 2 schema. Next part is the projection configuration can compose other projections. So I can define an inventory projection, and I can define a product projection, and I can include my inventory projection in my product, and then I can have a composed projection to include product. Third one was I included a state on my projection so that I can manage the release of these projections and the life cycle of those projections. So with all these tools in hand, I can manage a very large set of backing services who all want to operate independently. And I can manage a large set of customers who all have their own needs and need new features today. And I can roll out those new features today. Now I'm going to hand over to David, who's going to talk about how we are able to test all these schemas that are coming out.
Thank you. Hi, everyone. Today I'll be talking about some of the work that we're doing to leverage generative AI for improving test code coverage. As you've seen, we have scaled out our API surface tremendously across different versions and different projections. So we want to be able to use automated testing to sustainably manage the quality and performance of our services. I want to stress that we're still relatively early in our investigations, but I wanted to share some of the techniques and lessons that we've learned so far using AWS Bedrock that you can also apply to your own work. So let's begin by defining our problem statement. Given a particular API definition, how do we comprehensively test the composed methods in a sustainable fashion? Now, when I say comprehensively, I'm talking about 3 key areas: testing all of the API success paths, failure modes, and error conditions. I want to explore the parameter boundaries, and I also want to examine composed API scenarios. So we have to balance this against sustainability. So we have several factors that we need to take into account. The first is the cost to develop, and maybe more importantly, the cost to maintain these tests in an ongoing term. We also have to think about the resources required to run these tests, and perhaps most importantly, the code, the ability to understand them. When a test fails, we want to be able to tell quickly if it's due to an issue in the test or if it's due to an issue in the underlying service. So by leveraging AI, we want to enhance our ability to create these thorough tests while also making them more maintainable and interpretable. We have to maintain this balance throughout our API testing. So before diving into that, I just want to briefly discuss our API validation approach. So we leverage GraphQL directives on field constraints, which can provide declarative validation and establish a shared data contract with our clients. These directives help improve our data integrity by minimizing the downstream inconsistencies, and they standardize the error responses across our API projections. So let's just start with one of the example schemas from before. Now, leveraging directives, you can see that we can define constraints like a min and max on string length, or that the string has to match a particular regex pattern. It's not shown here, but you could also imagine doing this for other primitives like numerics. So with that primer out of the way, let's start by understanding the 2 steps that we use in our generative AI process. With our first step, we generate test case descriptions from the API definition, and we add additional instructions or context. Now in step 2, we transform these descriptions into actual test code. We split this into 2 steps for several reasons. It separates the what from the how, allowing us to optimize the test case coverage and the test code generation. We have flexibility to do this independently, so it also helps us optimize both without necessarily enforcing constraints on the other. It aligns with best practices that a test engineer might leverage in their design, where we want to plan our tests before we fully code them. So in the following slides, we'll explore 2 approaches to test case generation, and then dig into the code generation. So looking at how we would implement this using a traditional method for comprehensive API testing, our goal is to systematically cover every aspect of our API, so the strategy is pretty straightforward in concept. We walk through the entire API schema, examining each operation, argument, and validation conditions. For every possible combination, we want to create an integration test. This approach ensures that we're not just testing the happy paths, but also the edge cases, the boundary conditions, and these error scenarios. So it's thorough and methodical, but as we'll see, it comes with its own set of challenges. So here's a simplified Python implementation of our schema. This is pretty similar to pseudocode, if you will. The main function, generate tests, iterates over each operation in the schema, and then for each operation, it generates a happy path case and dives into testing the inputs. Now, looking closer at the test inputs function, this is where things start to get interesting and also complex. It examines each argument, generating the test for basic scenarios like missing required fields or wrong data types. But the key challenge here is handling nested composite types. So for these, we need to recursively apply our test generation process. This recursion lets us be thorough in our testing, but it also significantly increases the complexity of our test suite. If any of these input structures have special relationships between data fields or other considerations, this also needs to be hard-coded at this point, increasing both the initial coding and maintainability cost. So what are the trade-offs here? So on the positive side, we achieve our primary goal, which is comprehensive and systematic coverage of the API schema. Test case generation is, for the most part, deterministic and reproducible, with relatively fast execution time. We don't rely on any external service for this, so this keeps our testing process self-contained and reliable. However, there are significant challenges to consider. Implementation is time-consuming, and ensuring correctness of the test generation logic requires substantial effort upfront. The complexity of traversing the syntax tree also makes the code difficult to maintain and update. The rigidity of the approach means that we can't easily anticipate any unexpected scenarios or particularly complex scenarios. So you kind of have to think about these things up front, which is very hard to do when you're testing. And then lastly, while our coverage is comprehensive, it's not always intelligent about which comprehensive of inputs are most likely to uncover actual errors. So starting again from this problem statement, we want to now leverage generative AI. The difference here is that we're leveraging the power of a large language model to interpret our API schema and generate these comprehensive test suites. So let's again start with a simplified Python implementation. This function encapsulates all the major parts of our AI test-driven process. It takes our GraphQL schema as input and returns a comprehensive set of tests. So let's start to break this down a bit. Our describe schema function is the first step in the AI-assisted approach. It creates a concise description of our GraphQL schema. While we could just use the full definition, this abbreviated version highlights key elements for test generation, which are the types, fields, arguments, and validation rules. This provides the AI with just the essential context about our API structure and constraints, enabling it to generate relevant tests without getting overwhelmed by the full schema complexity. The next step is to craft a detailed prompt for the AI. This create prompt function takes the schema context and the specific operation that we want to test and generates a comprehensive instruction set for the AI. This prompt includes the schema description followed by clear directives for the types of test cases we want the AI to generate. This includes happy path cases, as well as the edge cases, missing required components, the list goes on. We'll dive a little bit more into the prompt engineering, but for now, we're just going to continue explaining the code here. So the ask AI function takes our carefully crafted prompt and sends it to the AI model. In this case, we're just using the Converse API for Claude Haiku version 3.5 on Amazon Bedrock. The language model will then generate a set of test cases based on the information that we've provided. Finally, and this is maybe one of the more important parts, we wanted to validate the test that we get. Our validate test function focuses on validating the structure and the content of the AI-generated test case descriptions. So key here is that we can't actually execute the test yet because we haven't generated the code, but this does ensure that our test case descriptions are well-formed and align with the API schema. So now let's talk about prompt engineering. The prompt structure is the key to the AI-driven approach. We have 4 crucial parts here. The schema context, which, as I mentioned earlier, is the API definition. The operation or operations that you're testing. The test requirements, where we outline the types of tests needed. We want to cover, again, both success and error conditions. We want to include boundaries on min and max, as well as right outside those limits. And finally, the output format. This is what lets us use the output from the LLM programmatically. But we can do a little bit better. So when crafting this prompt, sorry about that. If you recall, one of the requirements that we have is to generate comprehensive test cases for our API. So to achieve this, we found that we can actually invoke the LLM multiple times in a loop to iteratively generate new cases if we make some changes to the prompt. Especially when working with the latest models, we found that this approach helps ensure that we cover all possible scenarios and edge cases. So here, you can see that we've made a few changes to the prompt. We're now passing in the working set of the generated tests or previously existing tests as an intermediate state. We're also explicitly asking the LLM to generate new test cases and indicate when it believes it is done. But we can still do better. We're going to talk about how we can incorporate an advanced prompting technique called chain of thought into our approach. Chain of thought prompting encourages the AI to break down its reasoning process and explain its thought process step by step. So here, you can see that we've expanded the instructions to generate tests. By structuring our prompt this way, we're essentially asking the AI to show its work, much like you might ask a student to do with a math problem. This approach has several benefits here. So by first asking the LLM to analyze the operation and determine the test objectives, we ensure that it fully understands what needs to be tested before it starts generating the test cases. As the LLM provides its reasoning for each test case, it might actually uncover additional scenarios or edge cases that it didn't initially consider. It also provides transparency to us, the code writers, because we can understand the AI thought process, how it got to the output, and we can use that as feedback to make further updates to the prompt or the other instructions. And finally, it mimics how an experienced QA engineer would take a structured approach to test design. So altogether, applying these techniques results in a much more robust and comprehensive set of test cases for the GraphQL APIs. So now let's consider the trade-offs for the generative AI approach. So on the positive side, the method offers significant adaptability. The AI can quickly adjust to different API structures or even API languages without requiring extensive code changes. And it excels at creative test generation, often coming up with test cases that a human might overlook. The approach can dramatically reduce the initial development time as we're leveraging the AI's pre-existing knowledge rather than coding everything from scratch. As mentioned a little bit earlier, it's also particularly adept at handling the complex scenarios and API compositions that the programmatic approach has difficulty with. Moreover, there's potential for the AI to learn and improve over time, especially if we feed it the output from executing the tests or any discovered bugs or new edge cases. Now, for the trade-offs, one key consideration is the expertise required in prompt engineering. This is net new for a lot of teams that are coding today. Getting the best results from AI often demands skill in crafting effective prompts, which can be a new challenge. There's also the potential inconsistency in results to consider. Unlike the fully deterministic nature of programmatic enumeration, the AI might generate slightly different test sets each time it runs, which can impact your reproducibility over time. There's a dependency on an external service, so this introduces some potential failure points outside your control. And lastly, the quality of the generated test can vary based on the AI model used and how well it's been trained on similar tasks. So now let's go into how we actually go from test case to test code. For this, we explored both templating and generative AI approaches for the task. Interestingly, the methods follow a similar core process. So for template-based code generation, you supply test code templates in addition to your API test case descriptions into a template engine and use that to generate your test code. Now, for LLM-based generation, we still need the API test case descriptions, but now we use an LLM. We use example test code, not a template, and a prompt to guide the generation. Similar to the test case description generation, the templating rigidly relies on predefined structures, while generative AI actually provides us a lot of flexibility and adaptability here, at the risk of introducing more errors. One of the ways that we minimize those errors is to introduce a feedback loop in the generation. We found that this adds latency to the overall approach, but it significantly improves the quality of the results, and it's not something that you can automatically do with a templating approach. So now let's walk through an end-to-end example. Here we see a GraphQL schema for a new mutation operation called create product, and a product input and price input types based on our previous product type example. On the right, this is what we expect from running the Generate AI test cases on the create product mutation. Each test case includes a full set of input fields matching the product input structure. The first test ensures that a valid product can be created. And the second test, the title length validation. These test cases are directly derived from the schema and the mutation definition. So we want to make sure, again, that we cover both success and failure operations. So this slide shows now how we go from the test case description into a Python integration test. On the left, you have the test case in that JSON format, specifying the operation, the input data, and the expected outcome. On the right, we see the corresponding Python test. The test constructs the GraphQL mutation, sets up the input variables, and executes the query. It then verifies that the response matches the expectations. So we ensure that the product in this case is created successfully with the correct data for the first case, and that we get the right error response in the second case. So as we wrap up our discussion, I just want to focus on some key takeaways that highlight the most valuable aspects of this approach. The first is that GraphQL constraint directives are actually a pretty powerful tool for informing automated test creation, in addition to informing clients how to use your APIs. Secondly, we talked about the differences between programmatic and generative AI test case creation and the test code generation, where GenAI provides an alternative to templating techniques. Third, we've seen that proper prompt engineering is absolutely crucial. By making edits to the prompt, we can dramatically improve the quality and comprehensiveness of the generated test cases. And lastly, I do want to mention that while AI brings creativity to the testing strategy, we shouldn't completely disregard the programmatic enumeration. The realization we're approaching is that there's actually a synergy that you can get from combining both GenAI and some programmatic enumeration. The programmatic approaches ensure that you systematically cover all of your known scenarios and API constraints, while the AI can fill in the gaps. So these are some of the things that we're looking at as next steps. First, we're exploring techniques for chunking large schemas. Many of the real-world APIs are complex with hundreds or even thousands of operations and types. So by breaking these down into manageable segments, we can focus the AI's attention on specific areas, improving the quality of the generated tests, and working around token limitations with API calls. Next, we're moving beyond single API testing into multi-API interaction scenarios. So again, in that prompt engineering, where we have one operation, we're expanding that to include multiple. This lets us generate test cases that don't just test APIs in isolation, but cover integration issues. Third, we're looking at creating a more robust feedback loop, where we are able to pass the test code execution into the test case description creation, improving the output in the first step. And then lastly, we want to start exploring context-aware test evolution, where instead of having to invoke this manually, we're able to have the generative AI trigger on any updates to the schema, incoming bugs, things like that to expand our test suite. So just want to thank everyone for coming to our presentation.